In a saturated solution, the solid is in equilibrium with its dissolved ions. If we use silver chromate as an example, the solid silver chromate is the reactant, and the silver and chromate ions are the products. The common ion effect occurs when one of the dissolved ions is added or is already present in the solution. In this example, sodium chromate is added. It's an ionic compound, so it'll dissociate into its ions. But sodium isn't part of the equation, it's a spectator ion, so we'll just cross it out. The chromate ions are part of the equation, and adding them increases the concentration of chromate on the product side of the equation. That causes the reaction to shift to the left, making more solid precipitate. Let's start by calculating the molar solubility of silver chromate without the common ion effect. Cross out the reactant because solids don't affect concentration. Start with 0 products initially. We don't know the change yet, but we do know that it should follow the stoichiometry of the reaction. Determine the equilibrium concentrations. Then plug them into the equilibrium expression to solve for S. Now let's calculate the molar solubility of silver chromate in a 0.1 molar solution of sodium chromate. Cross out the reactant because solids don't affect concentration. We'll start with 0 silver initially, but this time we're starting with an initial concentration of 0.1 molar chromate. The change follows the same stoichiometry, so the equilibrium concentrations are 2S and 0.1 plus S. Now if you plug this into the equilibrium expression, it's difficult to solve, but here's a trick that will make the problem easier. We know that K is very small. In this case, it's 9 times 10 to the minus 12. Since K is products over reactants, if K is really small, that means the amount of products is really small. If the amount of products is really small, that means there's very little solid dissolving into its aqueous ions, so the change, or S, is really small. In fact, S is so small that when you add it to 0.1 and round it, you still get 0.1. So compared to the initial amount, S is considered negligible, which means we can omit it from the equation. I like to use the example of adding a pinch of sand to the sand at the beach versus adding a pinch of sand to a clean floor in your house. If you add a little sand to a clean floor, it's noticeable. It's worth taking into account because you can feel the difference between just a little bit of sand on your floor versus no sand at all. But if you add a pinch of sand to the sand at the beach, it's really not noticeable because there's already so much there to begin with. So the addition of that small amount is negligible compared to the initial amount that you're starting out with. In the example, we'll count the small amount of silver that dissolves because it's a noticeable difference compared to what you started out with, which was no silver at all. But we'll omit the amount of chromate that dissolves because it's negligible compared to the amount of chromate that's already there, which is the 0.1 molar concentration. Now plug in K and the equilibrium concentrations and solve for the molar solubility, or S. Molar solubility is 4.7 times 10 to the minus 6. If you compare this to the molar solubility we calculated earlier, you can see that molar solubility decreases significantly in the presence of a common ion. That's the common ion effect.